Warning: Oleum, or fuming sulfuric acid, is extremely corrosive. Wear gloves and protective clothing when handling it. The fumes are corrosive and possibly carcinogenic. This experiment must be performed outside or in a fume hood. This experiment should only be performed by an experienced chemist. It's been years since I gave a warning like that, so please don't take it lightly. Greetings, fellow nerds. This is a lab notes video on making oleum by amateur means. This video is a natural follow-up to my previous video on distilling sulfuric acid, so watch the original to have a bit more context. Links are in the video description. And I'll tell you up front that I was successful and just needed simple chemicals and a ceramic hotplate. But the yield was only about 13%, so it's not yet viable for amateur reproduction. Being a lab notes video, I'm not going to do a full safety analysis, so there are plenty of omissions. Therefore, please don't attempt it just yet. I'm still improving the method and learning the idiosyncrasies. For those of you that are unfamiliar, oleum is sulfuric acid with additional added sulfur trioxide. It's also called fuming sulfuric acid. The most obvious difference gives it its name. It fumes on air. The fuming is from sulfur trioxide evaporating due to its high vapor pressure. Oleum is viciously corrosive, and the free sulfur trioxide makes it easily sulfate organic compounds. It's a powerful dehydrating agent and in many ways behaves like boiling sulfuric acid, but at room temperature. It's somewhat infamous in chemistry for being one of the key precursors to many types of explosives along with nitric acid. I personally have no use for it, but I would like to make some because it's a synthetic challenge to do so by amateur means. Usually it requires very high temperatures or exotic chemicals. It's normally made in the industry by the oxidation of sulfur dioxide with oxygen over a platinum or vanadium pentoxide catalyst to make sulfur trioxide, which is then led into sulfuric acid. This is difficult for the amateur as it requires control of gaseous chemicals at high temperatures, but it has been done. The three common amateur accessible methods are the pyrosulfate method, the phosphoric acid method, and the tin sulfate method. In the pyrosulfate method, sodium persulfate or sodium bisulfate are heated high enough that they decompose into sodium pyrosulfate, and then heated further until they decompose again into sodium sulfate and sulfur trioxide. The sulfur trioxide is led into sulfuric acid to make oleum. This method requires very high temperatures past 600 Celsius, and so many amateurs avoid it. But it's cheap and doesn't require exotic chemicals. Although it may require quartz glassware, which is itself very expensive. In the phosphoric acid method, phosphoric acid is heated until it decomposes into various polyphosphoric acid polymers and then mixed with sulfuric acid. The powerful dehydrating properties of polyphosphoric acid rip apart the sulfuric acid into sulfur trioxide and phosphoric acid. The sulfur trioxide is led into sulfuric acid to make oleum. This method requires much lower temperatures than the pyrosulfate method, but phosphoric acid at these temperatures still damages glassware. So it's avoided by amateurs and even professionals because decomposing your glassware is a tremendous safety hazard. The tin sulfate method is simply the decomposition of tin 4-sulfate. This occurs at modest temperatures, but making tin 4-sulfate under anhydrous conditions is tedious, and tin itself is somewhat expensive compared to the resulting sulfur trioxide. So it's more of a curiosity or challenge project rather than a preparatory method. Finally, the professional approach to make sulfur trioxide, other than to buy it, is to react sulfuric acid with phosphorus pentoxide. This happens at relatively mild temperatures. The problem with this method for the amateur is that phosphorus pentoxide is a rather exotic substance and not readily accessible by amateur means. So my challenge is to make oleum by amateur means using common chemicals and hopefully at lower temperatures than the 600 degrees necessary for pyrosulfate. And on top of that, the glassware must reasonably survive for safety reasons. So to do that, I devised a modified pyrosulfate method that could operate at more modest temperatures accessible to the amateur. This method has been sporadically mentioned in the amateur chemistry community, but details are scarce and not much research has been done on it. So hopefully this video will be able to greatly add to the body of knowledge. The first step is to actually make sodium pyrosulfate. I set up a ceramic hotplate in a plastic bin for safety. The plastic bin is meant to slow down any flood of molten salts in the event of an accident and give me time to escape. A better containment system is a steel drain pan or a steel tray with deep sides. Anyway, I'm using a ceramic hot plate because I need the 540 degree temperatures it can provide. The standard aluminum hot plate that only goes to around 340 degrees is not hot enough for this experiment. Similar to my distillation of sulfuric acid procedure, I use a single unit distillation and condensation column, and I'm sealing the joints with PTFE pipe threading tape. I found this to be cheaper, easier to get, and more reliable than high temperature grease, and for oleum, even the high temperature grease seems to degrade. So I assembled all of that together onto a 1 liter Erlenmeyer flask. And to that flask I started with 400 grams of sodium bisulfate monohydrate, which is sold as a pH lowering chemical for swimming pools. Then I insulated the flask with aluminum foil to keep the heat in. We need to get as high temperature as possible. Now I turn on the cooling water and turn on the hot plate heating to 200 Celsius at first, and let it warm up for half an hour before raising it another 100 degrees every half hour until we reach the maximum limit of the hot plate. This slow heating rate is to prevent thermal shock of the glassware. So what we're doing is drying the sodium bisulfate and removing the water. At first we're just removing the water of crystallization, but as we get hotter and hotter we reach a point where we pyrolyze the sodium bisulfate into water and sodium pyrosulfate. In theory, if we go high enough, the sodium pyrosulfate itself will pyrolyze and release sulfur trioxide. And if you see fuming in the flask, then maybe you have. But I was not able to get there. My 540 degree ceramic hot plate should in theory get hot enough to do so, but the thermal transfer is limited. Also, the amount of sulfur trioxide formation is really only appreciable at above 600 Celsius. Below that, the rate doesn't seem fast enough to be useful, or in my case, even detectable. Since the temperature isn't as uniform as, say, a furnace, I wouldn't be surprised if it was only 400 Celsius in there, not hot enough to pyrolyze the sodium pyrosulfate. You might be wondering why I'm not using a stir bar to keep the temperature uniform and prevent bumping, something that sulfuric acid is prone to do. The reason is that at these temperatures, even my highly resistant PTFE stir bars start to soften and break down. I'd have to have a glass stir bar, and even then the temperatures start to demagnetize them. So I'm making a point not to use a stir bar for the pyrolysis step. Interestingly enough, I found the molten sodium bisulfate to be somewhat well behaved. While it does boil, the bubbling is light and doesn't seem to throw up a corrosive cloud of face-melting death like the sulfuric acid does. That being said, your particular sample may behave differently, so be careful. It's still molten corrosive acidic salt. Nonetheless, the lack of a stir bar or boiling chips isn't the explosive bumping disaster it could have been. Anyway, I kept heating for several hours, and I even had to further insulate the flask with more foil to squeeze out as much water as I could. All the while, I wasn't able to produce any sulfur trioxide. At least not yet. After several hours, I stopped heating and let it cool. And there it is. This should be sodium pyrosulfate. But I wouldn't be surprised if it was still mostly sodium bisulfate. We didn't see any fuming as we heated it, so we didn't get to the point where sulfur trioxide was being liberated. This is where most amateurs stopped. To make sulfur trioxide, the temperatures needed to be pushed further, around 600 Celsius. This has been successfully done with better equipment, but this ceramic hot plate is just not hot enough. And there the problem stood. If we can't thermalize out the sulfur trioxide directly, we'll have to do so indirectly. The reason why I let it freeze is to add in 150 grams of concentrated 98% sulfuric acid that we distilled in a previous video. If we add it in while hot, we ran the risk of it boiling and splattering on us. Anyway, we also drop in a PTFE magnetic stir bar to reduce bumping since we're going to be heating sulfuric acid now. Although I did find out later that the mixture was still well behaved even without a stir bar, so I think the stir bar is optional. Anyway, we reinstall the condenser, change out the receiver, and once again we start heating, but we go a bit slower this time. We first start at 200 Celsius and then raise to 400 Celsius over the course of an hour. Once the whole mixture melts, we gradually raise the temperature 15 degrees every 10 minutes. I noticed at about 490 degrees it started to fume. This is a great sign. That is oleum distilling over. The first several drops I collected I discarded because the condenser still has water condensate from the previous dehydration step. In this new receiver, we are collecting oleum. And that is amazing. The fuming that happens with oleum is so much denser than normal acids, so it'll be pretty obvious when you have it. Not going to lie, I'm surprised this worked. Almost all other amateur methods involved furnace-level temperatures, phosphoric acid, or exotic chemicals. I honestly didn't think something as simple as a ceramic hot plate along with some sodium bisulfate could actually make oleum. This is working so well that we're actually solidifying sulfur trioxide. Sometimes this will solidify in the condenser and clog it, so you'll need to stop cooling and hit it with a heat gun to melt it down before resuming cooling. Here we're lucky in that it's solidifying at the end of the condenser. Okay, so why does this work? Presumably the pyrosulfate method requires 600 Celsius or higher, and the phosphoric acid method destroys glassware. How are we able to do this without either? Basically, once we produce sodium pyrosulfate, instead of heating it further to liberate sulfur trioxide, we react it with sulfuric acid to produce sodium bisulfate and oleum. I'm not sure how far the equilibrium actually goes, but it doesn't matter. Oleum is actually quite volatile and easily boils out the sulfur trioxide, driving the reaction to the right. So this method is essentially working by converting a highly stable sodium pyrosulfate into highly volatile fuming sulfuric acid and boiling it out that way. This doesn't require nearly as high a temperature as directly trying to rip sulfur trioxide from sodium pyrosulfate. The massive drawback is that you still need to make the pyrosulfate. Additionally, this method is not a way of making sulfuric acid. If we could make the sulfur trioxide by itself, then we could make sulfuric acid, but the sulfur trioxide produced here requires that we consume sulfuric acid. But this is still an amazing result. And as said before, I honestly didn't think it would work. One problem though is that I don't know when to stop the distillation. It seems that we're distilling off oleum with high sulfur trioxide content first. As that distills, the sulfur trioxide content of the distillate will decrease until we're just distilling sulfuric acid, and then we'll finally start distilling water in increasing amounts because we'll begin dehydrating and pyrolyzing the sodium bisulfate. Industrially, the distillation of oleum is monitored through measuring the dielectric constant of the distillate. Unfortunately, I don't have a glass dielectric constant measuring system, but interestingly enough, such a system is actually well within the capabilities of even a novice electrical engineer, so maybe someday I'll give it a go. But for now, I'm going to simply watch for the solid sulfur trioxide to start shrinking rather than growing. If it's shrinking, that means it's getting dissolved by the sulfuric acid. And it looks like it's happening now. Unfortunately, the rate was too slow for me to notice, so it wasn't until a substantial quantity had dissolved that I finally realized and switched out the receivers. Once I collected what I thought was the oleum, I then changed out the receivers and stopped with the flask containing the oleum. Now, to clean up and regenerate the sodium bisulfate, I turned off the power and let it cool far enough that it was no longer distilling and fished out the stir bar. Unfortunately, it was still so hot that my magnetic stir bar retriever partially melted. So I'll probably need to get or make a glass encapsulated stir bar retriever before trying this experiment again. Anyway, after the stir bar was recovered, I put the apparatus back together, cranked the heating up to maximum, and distilled over all the remaining sulfuric acid water. Basically, I'm regenerating the sodium bisulfate by boiling out the acid and pyrolyzing it again. The sulfuric acid I'm collecting now will be less concentrated, and it will contain the water being pyrolyzed out. But it's still going to be 80 to 90%, so don't be complacent. Treat this acid with the same respect as concentrated acid. This acid can be repurified into concentrated sulfuric acid as shown in my previous video on the subject. Meanwhile, the regenerated sodium bisulfate can be reused to make more oleum. That's the great advantage of this process. It's essentially catalytic and overall it just separates the water from sulfuric acid to make sulfur trioxide. Although granted, with the tremendous amount of labor involved, it certainly doesn't feel like a cheap method. At this point, if you're still with me, I'd like to ask you to subscribe, leave a like, and possibly leave a comment. The YouTube algorithm is an insatiable monster that must be fed. Additionally, I have a Patreon if you think I'm just that good and worth supporting. Anyway, here we are after all the distillation is done, and this is the receiver containing the oleum. At first we could see chunks of undissolved sulfur trioxide, but all these dissolved after some shaking. Just by looking at it like this, it doesn't seem all that impressive. It just looks like regular sulfuric acid, except maybe a bit more viscous. You'll notice though that I'm using a glass stopper wrapped in PTFE pipe threading tape to plug the flask rather than my usual vacuum grease. This is because sulfur trioxide is corrosive even to vacuum grease. But the real anxiety-inducing reason for its fuming sulfuric acid name comes when you open it. And that is kinda terrifying. That ominous mist is the sulfur trioxide evaporating from the glass stopper and absorbing water right from the air. The droplets that form are sulfuric acid and big enough to be seen as this ominous mist. It's also rather corrosive and will burn your lungs from the inside out, so you have to handle oleum in a fume hood. I transferred to a vial to weigh and found the quantity to be 29 grams. But that's not the yield, since a fair amount of it is sulfuric acid that was also distilled over. So to measure the amount of sulfur trioxide produced, I titrate it against a sodium carbonate standard. First, I weighed a quantity of oleum and diluted it into a known quantity of water. I did this in a flask to contain the mist and waited an hour for it to completely settle. The reason why I did this is because if you try to titrate oleum directly, it fumes so badly that a significant amount of the acid is lost and you get a horribly inaccurate result. So diluting it first is necessary, along with taking steps to capture and redissolve the mist. Something I want to show you is what happened to the latex pipette bulb. The inside got charred just from exposure to sulfur trioxide fumes. I have a new one for comparison. The bulb itself did not touch the actual acid, just the fumes. This will be your lungs if you inhale this, so this is why you absolutely have to have a fume hood to handle oleum and sulfur trioxide. Anyway, once I had the diluted acid, it was titrated and I found the concentration to be 112% sulfuric acid equivalent. What this means is that the oleum behaves like it's 112% sulfuric acid in a titration. It's higher than 100% because sulfur trioxide has a molar mass less than sulfuric acid, and thus it becomes more sulfuric acid when reacted with water. So to convert this 112% sulfuric acid equivalent into free sulfur trioxide, we use this equation and we get 53% free sulfur trioxide. Thus, of the 29 grams of acid collected, about 15 grams of that is sulfur trioxide. We expected 115 grams from the 400 grams of sodium bisulfate, so the yield is about 13%. For the first attempt of a new procedure, I think that's pretty good. And I think I can improve that further by finding a way to better heat the reaction and convert more bisulfate into pyrosulfate. Maybe I just need more insulation or a better hotplate. I tried to use a domestic kitchen hotplate since I didn't need stirring, but the hot spots shattered my flask. So that was an expensive lesson. Another idea is to add oleum back into the pyrosulfate for the next run. This does not increase yield, it just adds them together. But it would help us increase purity for the next run. Alternatively, it may be possible to directly fracture distill the oleum to get relatively pure sulfur trioxide. But I'll need a lot more than this to test that. But while we're here, let's test the stuff. First thing I'm going to do is to drop some on this tissue here. And that is terrifying. It almost instantly burned and charred it. This is like sulfuric acid on steroids. Now I'm going to drip it on these nitrile gloves. The acid does seem to burn the gloves, but the integrity is maintained. It didn't instantly destroy them. It seems there is enough resistance to allow for time to strip off the gloves in the event of a spill. So I'll continue using nitrile gloves, although I'll probably get some thicker ones. Do you guys have any suggestions for other things to test this on? Let me know in the comments. Since this is a lab notes video, I can drop some notes on stupid things I did. I tried to make acetic anhydride by reacting the sodium pyrosulfate with glacial acetic acid. The idea is that the pyrosulfate would dehydrate the glacial acetic acid. Unfortunately, that didn't work as the boiling point of glacial acetic acid and the melting point of sodium pyrosulfate are too far apart. I was hoping it would dissolve and react that way. Oh well, at least I tried. Anyway, that was my first attempt at making oleum. It's not yet viable for wider amateur use, but I think some improvements can be made. If I can get the yield up to 30% or even 50%, then I'll make a proper synthesis video. So until then, please don't actually copy my procedure unless you're trying to improve the synthesis as well. It's still a work in progress. One thing I need to cover is proper storage and disposal procedures. This stuff is nasty. Thanks for watching. And special thanks to my Patreon supporters. Without you, I'd be severely limited in the sorts of experiments I could do and the resources I'd have access to. Thank you very much for your support all these years.